Hello, this is Andy Schweitzer. This is a final video on what I call the molecular view of kinetics, trying to explain what happens in a chemical reaction that might explain why a reaction runs faster or slower. There is a PowerPoint associated with this. It's a little more detailed, gives a few more examples. I'm just going to run through the nuts and bolts of these topics. Okay. First thing that we look at when talking about molecular view would be what's called activation energy. Okay, now I could take a molecule, let's say for example carbon, carbon double bond to another carbon, and then this carbon could go here. Now this is called a cis 2-butene. We can rotate this molecule around to form carbon, single bond carbon, double bond carbon, and then this, rather than being crunched, it would go, well, I drew this a little bit backwards, but I'm just going to draw it straighter here. We might call it trans. And in reality, it would look more like this, and then it would look like this, like that. Okay, using another way to show each corner is a carbon bond. So when I rotate this around at the top, I should have drawn this one down slight here to begin with. But either way, this is just a single individual element, a molecule going through some sort of manipulation or chemical reaction. For this reaction, we would have a simple starting point energy, and energy needed to break this double bond, and then rotate it around, and then energy would be released. The trans configuration is usually more stable, therefore lower energy, and therefore this reaction would be exothermic. When we break that bond, there's a certain point where it's the hardest, most energy you put into it to try and snap this double bond so you can rotate it. That would be this point right here. This is the hardest, most energy needed to be invested in order to get this to work. Now, the activation energy is from the start to the peak. This is called your energy of activation. Okay. It's always start to peak, regardless of the reaction. Now, the total energy released here, now this is just a not to scale drawing as far as how much energy is actually released here. Not a big time release of energy in this chemical reaction, it's slight. But it is going to be the delta H would be the energy that's being released. Okay. For a different chemical reaction, we might have a reaction where we put energy in and it comes out. This would be an endothermic reaction. At this point, we'd have our energy of activation right here, and then from here to here would be your delta H. For this guy, delta H would be negative, meaning energy is being released to its surroundings. Here, it'd be positive, energy needs to come into the chemical reaction. And away you go. So, next up here, rate laws. Okay. Now, I have a couple different examples here. If I were to take a chemical and just react it, very similar to what I just did, some chemical. This, if I doubled the concentration of A, then the rate doubles. That's really all it is. The rate is equal to constant K, A, single. I could take A reacting with A, and I'd basically have to slam two A's together. At this point, rate A equals the constant K, and then this thing would be A to the second order. Okay. Now the overall order would be 1 here and 2 here. I could take A and slam it into B. Right. Again, if I double the concentration of A, my rate doubles. If I double the concentration of B, my rate doubles. So rate equals K, and then it'd be concentration of A, first order, concentration of B, first order, and overall second order. These are all very common types of chemical reactions. I could, however, have a reaction where I go A, I have to slam, let's say, 3 A's together. This is going to be rate equals K, A concentration, and I'm going to just do it like this, A to the third. Third order overall. Or we could have A plus B plus C. 3 things needing to hit simultaneously in order for a chemical reaction to occur. Rate equals K, concentration of A, concentration of B, concentration of C. And it's third order overall, first order with respect to all of these guys. These 2 guys here, it's tough, you know. It's rare to have this type of chemical reaction. Now again, I'm using the coefficients of these individuals. So as I mentioned on previous videos, you know, we really can't, when you see a chemical reaction, let's just say 2A plus C plus a B yields E, F, and G, just hypothetically, okay? We can't just use our coefficients here as the rate laws. If I were to, the rate law orders, if I were to use this rate, okay, equals K, and then concentration of A, concentration of B, concentration of C, all right? I can't use these for that because I don't know if I'm looking at a one-step reaction. Now in this case, that would be 4 things coming together at one time. Literally impossible, okay? So I definitely know this chemical reaction is a stepwise reaction of maybe 2 or 3 or more individual, what we call elementary steps. Okay, which then would add up to my overall chemical reaction. Okay? And we'll see some examples of that as we go along. So, bigger, more complicated reactions, which we see all the time, okay, have to be a series of smaller steps simply by the fact that we can't have that many things colliding at one time. It's statistically impossible, okay, unlikely. And second of all, we can't use our rate law here because we don't know if we're looking at an elementary step. If we said this is a one-step reaction, however unlikely it is, then 2 would go here, 1 and 1, fourth order overall. But we just can't say that without more information. All right, so how do we go about using these elementary steps in order to produce a rate law, which we then can use to predict rates? Again, we don't want to do these things unless we can actually have some purpose for them. Our overall goal in kinetics is to predict rates of chemical reactions. Again, I will focus on this right here as far as determining orders. And I'll use this in the individual steps. So let's go to the next slide here and let's try some examples. Okay. Now, in this chemical reaction, I have taken the NO plus F2 yields NO2, and then that's called a slow step. And then we have F plus NO2 yields NO2F. Okay. So when I want to create my overall reaction, I take all of my reactants, put them over here, and I take all of my products, okay, put them over here, and cancel out things that are on both sides, okay, because that happens. So for this reaction here, I'd have an NO2, I'd have an F2, I'd have an F, and I'd have an NO2, another NO2 right here. Yields NO2F, NO2F, I have an F, I have another NO2F, and I'm done. Note that the fluorines on both sides, that would cancel as an intermediate. When I write my rate law out, I have to use the actual chemical reaction that occurs. I cannot use an intermediate in my rate law, mostly because, well, this is theoretical that the F occurs. Okay, all of these step-by-step reactions are our best guess at what happens on a molecular level. We can't see it. Okay, so rate equals the NO2 concentration, and then the concentration of F2. Now, without knowing any of my individual elementary steps or theorizing about it, I would say this is second order and this is first order, but I can't do that because we're assuming this is a first order, a single step reaction, which it's not. I need to use my individual steps. Now, the slow step is the step that controls the reaction. If I were to write out the energy activation chart for this, it would be as follows. I would have, okay, 2 steps, therefore 2 bumps, 2 activation energies. The first one would be the slowest. The slower your step, the bigger the crest on that activation energy. My second step would be slightly smaller. Okay? And I made it exothermic. Either way, the first step ultimately is the controller of the overall reaction time. It's not the actual reaction time, it's the one that just simply controls it. I can speed up this last step all I want. It's not going to fix the fact that we have a little bottleneck here. Okay? Either way, the slow step ultimately controls the step. So anything in this slow step or anything that can make that slow step speed up would in fact be helpful. Okay? So in the slow step I have 1 NO2, therefore I put a 1 here. It's first order. I have 1 F2, so I put a 1 right here, first order. It's first order with respect to NO2 because I have 1 NO2 in the rate determining step. This is the important part here, folks. I have 1 F2 in the rate determining step, so therefore I put a 1 there. And therefore this is my rate law for that particular substance. This is the equation I would use to predict the future rates of different concentrations, and I could test it to see the viability of, does it actually work? Next one. Okay, I got a couple steps here, and they're already added up for me. So again, the first step is slow, so I use that one. I can easily come up with my rate equation here. Rate equals K, and then I use my 2 reactants. O3 concentration, NO2, all right? And I don't know my powers, that's what I want to figure out. Use just your slow step. So O3 would be one of them, so I'll put a first order here. And then I have 1 NO2, so I'll put a 1 there. And again, I'm done. Okay, I cannot include the fact that, well, this isn't my intermediate, okay? But the fact that I have NO2 here, it's not, I don't put a 2 here because it is in fact not in the rate determining step. Only one of them is. Let's do a hypothetical example. Let's say we flip this to fast and flip this one to slow. Now the second one is the slow step. Now keep in mind, if I increase the concentration of the O3, that picks up the rate of this chemical reaction. And this example would look like this. Okay, where the first step is slow, it'd be fast, and this one is a little bit slower. The issue here is that if I can speed this one up, by speeding up this one, I can actually crank up the concentration of my reactants of my slow step. All right, again, I'm making this one slow. I'm reversing it. So it's kind of a domino effect where you tip one over, it causes the next one to go, which causes the next one to go. All right. So pay attention. The rate determining step is the slow step, and anything that feeds that slow step in order to speed it up. So if I increase the concentration of O3, that cranks up the concentration of NO3, my hypothetical intermediate, which then speeds up my slow step. If I increase the NO2, same thing. Feeds both of these, which then feeds this guy. So in this case, I'm going to make my rate law for this hypothetical situation as being this. Okay, same rate equals K, concentration of O3, concentration of NO2. All right, I'm going to include both of these steps because they eventually both will be able to speed the reaction up. 1O3, I have 1 NO2. I have NO3 here. It's not in my step-wise. It's intermediate. Can't use it. NO2. All right, and I got another one of those. Bump it to a second order, and I am done. This is my new rate law for if I flip it fast to slow. Final example, and then we will be done with this little video. Let's take a moment. Let's add everything up. Okay, this is not done for us here. If you want to try it yourself, okay, you can try it out. I have 2 N2O5s. I'm going to draw my arrow here. I have 2 NO2s. I have an two NO3s. I have an NO2. I have an NO3. I have an NO. I have another one of these guys. Bump this up to a 3. And then I have an O2. All right, now we have another NO3 here. I'm going to bump this up to a 2. And then we have another NO here. Okay, and then I have 2 more NO2s here. That bumps that up to a whopping 5. Cancel out like options here. We have this guy cancels this guy down to a 4. My NO cancels out here, and I get my overall reaction 2N2O5 goes to 2NO3 plus O2. My rate law would equal my K and then N2O5. Okay. At this point, my slow reaction is going to be the second step, all of which are containing intermediates. So at that point, I use the slow step and everything that feeds the slow step. 2 of these guys. There we go. And that is it. This thing is done. Just to start, get people moving on some of this stuff. Try some examples, ask some questions. Thanks a lot.